All right, so we are all done with convection now, and time to start our last section of the course, which is radiation. Kind of hoping we can do this in person at some point, but that's clearly not going to happen. So radiation, first thing we're going to deal with is basic outline of radiation, and then go into something called view factors. So first up, radiation, electromagnetic radiation emitted by a body due to temperature, and therefore it's electromagnetic radiation. So every object in the universe is emitting electromagnetic radiation based on its own temperature, and that is thermal radiation. That is a form of heat transfer. So because this is electromagnetic radiation, it has all the properties of electromagnetic radiation, such as traveling at the speed of light, frequency and wavelength related by this speed of light. C is wavelength times frequency. The energy for one photon is h times f, where h is Planck's constant, 6.63 times 10 to the negative 34th joule seconds. Has a momentum, hf over c. So all the standard electromagnetic basic equations. For our purposes, we're dealing with the thermal part of this, the energy transferred, heat energy transferred. What we get for that is an expression for the total energy emitted per unit area per unit time due to this thermal radiation. So our value at Q, for radiation, value at Q is written as EB a lot of times. This is basically the energy of a black body. We'll deal with that a little bit later. But my energy general form Q, heat transfer, is sigma times T to the fourth, temperature to the fourth power. Make sure this is in kelvins. This is the time of the course where that really matters now. For convection and conduction, got away with not having to convert into Kelvin, but now we really do. Then sigma, the Stefan-Boltzmann constant, 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the fourth. So again, this B subscript indicates that I'm dealing with a black body. Definition of a black body is an object in which all the thermal energy produced is allowed to escape. So this entire sigma T to the fourth energy is escaping the body. For most materials, some of it actually stays trapped inside, so not all of it actually goes away. There's usually some fraction of it that goes away. Those are not black bodies, but for black bodies, we're assuming it all goes away. So this entire energy, sigma T to the fourth, is what the object is giving up. Similarly, a black body is an object that absorbs all the thermal energy incident upon it. So again, every object in the universe is emitting and absorbing thermal energies from each other. And so a black body is going to emit this entire energy, sigma T to the fourth. It's going to have some sigma T to the fourth from other objects hitting it, and it's going to absorb all of that as well. Again, usually in real life, objects are not black bodies. They're going to not absorb all of it. Some of it will be reflected, some of it may be transmitted. So not all of it will be absorbed, but black bodies, we're assuming that is the case. So general case, when I have this incident radiation coming from another source, hits some object, some of it gets absorbed, like we were saying before. If it's a black body, I'm assuming all of it gets absorbed. But in real life, some of it gets reflected off that surface. Some of it gets transmitted through the surface. Most objects, the transmission is really close to zero anyway. Some of it will still get absorbed, some of it will still get reflected. A lot of it gets absorbed. And so a lot of the objects we deal with have a fairly high absorptivity, a relatively low reflectivity, and transmissivity almost zero. So a lot of times we can take the transmissivity to be zero, and that's what we'll be doing, especially for the first couple of weeks. Have a transmissivity of zero. So only a few things that actually you have to worry about transmissivities. Things like windows. You just think of normal light here. If I'm looking at a wall, I can't see through the wall, so none of the light is making it through the wall. Kind of same thing for thermal energy. A lot of barriers, nothing actually makes it through, but some could still get absorbed, some could still get reflected. A window, though, light does make it through the window, so that's kind of an example of energy being transmitted through. But again, most materials, that doesn't happen, or very little happens. So generally what we have is this combination of reflectivity rho, absorptivity alpha, transmissivity tau. Those all add up to 1 because basically all the energy has to go somewhere. Some of it gets reflected, some of it gets absorbed, some of it gets transmitted, and that's all my energy, so that all adds up to 1. And so all these things, rho, alpha, tau, are generally some number between 0 and 1. Emissivity, so again, this thing's leaving now. So reflectivity, absorptivity, transmissivity was radiation hitting an object and what happens to it. Emissivity, again, is that energy stored inside. That's going to want to get out, that's sigma t to the 4th. Again, not all of it goes out, but what they found is that emissivity is equal to the absorptivity. So whatever comes in is kind of equal to whatever goes out. So emissivity, absorptivity, epsilon equals alpha. Those are always the same number. Again, if I'm absorbing or emitting all my energy, epsilon or alpha equals 1. That means it's a black body, so that's another definition of a black body. If either alpha or epsilon equals 1. Now generally, again, we assign some numbers to these values, rho, alpha, tau, and epsilon. Those numbers are usually something like 0.7 or 0.8, 0.3, whatever it is. Technically, what really should happen is these numbers actually change with wavelength. So depending on what kind of electromagnetic radiation this is, whether it's X-rays, whether it's visible light, whether it's radio waves, these numbers are going to change. Kind of the same thing where X-rays can go through your body, but visible light can't. And so that's going to change the transmissivity, for example, because again, for X-rays, shorter wavelength, they go through more things. But we don't really deal with that. We just take it as, here's a number, assume that happens at all wavelengths. But for general purposes, it's good to know what actually does happen in terms of wavelength. And so usually you have a graph that kind of looks like this. Emissive power of a black body per unit wavelength is given by this function here, EB lambda. So again, this is the one that depends on my wavelength lambda. Has some constants in it, C1 and C2. Those depend on the properties of the material. It's not really worth too much getting into those, but there's just some constants. I have lambda to the -5th power, E to the C over lambda times temperature minus 1, and that gives you curves that look like these. So different temperatures gives me different curves. So obviously for higher temperatures, I'm emitting a lot more energy, emissive power, because again, sigma t to the 4th, t to the 4th power means my temperature 2000 compared to my temperature 1000 is going to be emitting 16 times, because factor of 2 to the 4th power. So 16 times more power here in the orange curve than the green curve. Another thing that's interesting about these curves is it's called Wien's law, which gives you the lambda max. So basically, where the highest amount of radiation is being emitted, what the wavelength is, times the temperature T of the object is actually just a constant, and that constant is 2,898 micrometer kelvins. So you can kind of see as temperature goes up, this lambda max is going to go down. So my wavelengths are getting shorter and shorter in terms of where the energy is being emitted. And you can see that on these graphs. A temperature 2000, peak wavelength is roughly 1.5 here. As I go up to 1500, it gets closer to 2. Up to 1000, I'm closer to maybe the 3 micrometer range. And so you can see this peak of these curves is kind of shifting to the right as temperature goes down. So that lambda max times temperature is just this constant value. Now the ones we saw before are kind of the ideal case. Again, I'm assuming that the emissive power doesn't change with wavelength, in the sense that it's just some constant number. And also that is a black body. So if I take this curve that I had before, this is the 2000 curve from the last graph, I assume that it was a black body, assumed that epsilon was 1. In real life, that may not be the case. I might have an epsilon of something like 0.5. If I have an epsilon of 0.5, it just means that I'm only emitting half of my energy. So instead of emitting this entire green curve, I'm emitting this yellow curve down here. So basically this yellow curve is just the green curve divided by 2 for an epsilon of 0.5. But again, in real life, it's not this nice smooth function, because this nice smooth function assumes nothing's happening. There's no change in epsilon with respect to wavelength. Epsilon's 0.5 for the entire thing. But what really happens, like I mentioned, is that as the wavelength changes, my epsilon value is going to change as well, and it usually changes in a fairly erratic pattern that is kind of indicated by this orange line here. And so you can see that down here, it's not really emitting much. Up here, it's emitting a decent amount, then kind of drops down a bit, jumps back up. And so that's kind of what a real emission spectrum is going to look like, but that's really hard to deal with. So instead of dealing with those, we take the integrated average. So integrate this orange guy over its entire wavelength spectrum, make that into a nice smooth curve, and that's this orange line here, or yellow line, I mean, for epsilon equals 0.5. So that's an ideal gray body. So black body, epsilon equals 1, nice and smooth. Ideal gray body, epsilon equals something else, but still nice and smooth. And a real body is this kind of jagged line. Again, for our purposes, we're going to consider these gray bodies as their integrated values. So we're going to deal with a nice smooth curves with some value of epsilon. If you go back to the curve we saw a couple slides ago, this guy here, these peak wavelengths. So you can see, again, for the high temperatures, I have a shorter wavelength. Shorter wavelength corresponds to different colors. Think of the visual electromagnetic spectrum for visible light. The shorter wavelengths, around 300, 400 nanometers, that's dealing with purple and blue light, whereas up around 600, 700, that's more red light. So you can see that kind of shift as I go to a lower wavelength, so it corresponds to a higher temperature. So that's why you kind of see when things heat up, eventually they start glowing red, because if at a low temperature, it's not emitting any visible light. Then you get to a high enough temperature, it starts emitting red light at that 700 nanometer wavelength. And then again, heating up more and more, it goes from red to orange to yellow. Eventually gets to white, because that's kind of all of them at that point is, add all the colors and you end up with white. Eventually you might get to all the way down to blue, because those red wavelengths aren't emitting anymore. So that kind of explains why that happens. A lot of times we care about how much energy is emitted in a certain part of the spectrum. So a certain wavelength, so how much is emitted between, say, 0 and 500, or how much is emitted between 500 and 800. And so what we have is this kind of ugly looking function in terms of diffraction. So EB from 0 to lambda, so some total energy being emitted between wavelengths 0 and some lambda that I care about, divided by the total. So EB from 0 to infinity. EB from 0 to infinity, again, is the total amount that's going to be emitted. So this is my fraction of energy emitted between 0 and lambda. What I want to do is take my EB lambda function, those nice smooth curves that we saw before, and integrate them. So find the area underneath them from 0 to the lambda I care about, and integrate it from 0 to infinity, gives me the total. So that again gives me that total function or total fraction of energy being emitted. Now, the good thing about this is we don't actually have to do these integrals. Someone's already done them, and the values are found in a table. So table 12-2 on page 554 to 555 looks something like this. So it depends on the value of lambda times T. So the lambda value that I care about times the temperature has some value. So let's say I want from 0 to this thing being 2000. So here's 2000. The total fraction is roughly 6.7%. So that tells me how much is emitted between 0 and that value. So it's going to depend on, usually I'm dealing with a wavelength, but also depends on the temperature. And it's usually only this thing that we care about, this column, this thing called F, 0 to lambda. That's that fraction that this whole thing essentially is called F0 lambda. So that's generally the only column I care about. These other columns just give you the intensities. This is the fraction versus the maximum. You can see that the maximum happens right at that 2898 value that we saw before. But again, this F0 to lambda column is really the only one we care about for this. So I just kind of gave a brief example of how to find it between 0 and some value. And sometimes you want it between two different values, say 500 and 800. So in that case, I just take the bigger one, subtract the smaller one. So I basically take it from 0 to 800, subtract from 0 to 500, and basically at that point left with from 500 to 800. The easy way to calculate this is to take EB from 0 to infinity. EB from 0 to infinity is the total energy emitted. Total energy emitted is sigma T to the fourth. So sigma T to the fourth, generally I know what the temperature is. Sigma is just a constant, so that I know that value. And then these fractions, again, look a bit complicated, but this is just that F value from the table for my higher wavelength. This is just the F value for the lower wavelength. So just find those two numbers, subtract them, multiply by sigma T to the fourth, and there's my total energy between those two wavelengths. So example of this, concrete example of this, I want to calculate the energy emitted between 4 and 5 micrometers by some gray body at 100 degrees Celsius with a emissivity epsilon of 0.6. So again, I want to find in the table between 4 and 15 micrometers. I want to, or I need to, in that case, find lambda times temperature. So wavelength times temperature, because that's what the table is given in. So wavelength 4 micrometers, temperature again in Kelvin, so 273 plus 100. And notice that in the table, I do have kind of weird units. It's not meters kelvins, it's micrometer kelvin. So keep these as micrometers, your wavelengths, when you do this. So 1492 is my bottom one. The higher wavelength, 15 micrometers, again, times 373 kelvins, gives me about 5,600 micrometers. So now I just have to look up for those two values in the table, again, called F0 lambda. So I go back to that table, look up 1492. 1492 is almost halfway between 1400 and 1600, not quite. So you're gonna have to interpolate this. So almost halfway between 0.0779 and 0.0197 something. So that's roughly 0.012. I actually did the proper interpolation in the question, but again, looking here between the two values, roughly 0.012 or 13, somewhere in that area. It's halfway between there. So proper interpolation gives me 0.01245. And then the second one, I had a temperature of almost 5,600. Table I had in the previous slide only went up to 4,400. It keeps going. I just cut it off there. So no point showing you the table. But that guy, 5,600, is roughly 0.7005. So total energy emitted, total energy, sigma T to the fourth. But sigma T to the fourth is for a black body. This is technically a gray body, so I have this value of epsilon in there as well. But that just goes outside. And then these guys, again, are the values found from the table. So sigma, 5.67, 10 to the negative 8, watts per meter squared, Kelvin to the fourth power. Epsilon of 0.6, temperature, again in kelvins, of 373 to the fourth power. And then this first fraction, my second wavelength was 0.7. This fraction, my first wavelength, 0.12. So subtract those two guys, multiply all that out, gives me 453 watts per meter squared as the emissive power in that case. So that is basic concept of radiation. So basic radiation, I have sigma T to the fourth, and there's a few things I add on to that. So like we just saw, I added on this value of epsilon if it's not a black body. And something else I'm going to need to add on is something called the view factor. So what happens with radiation is I have this body and it's emitting radiation, but it's emitting radiation in every single direction. So think of you as a person, you have some temperature, so you're emitting some radiation. Some of that radiation is moving in front of you, some is going behind you, some is going to the side. If I'm looking at the interaction between two objects, so if I'm looking at the interaction of, for example, me right now and my computer sitting in front of me, I have radiation coming off me in all directions. That total energy is sigma T to the fourth, but not all the energy is going to hit my computer because my computer is only in front of me. It's not going to hit any stuff behind me. So that's where the view factor comes in. It's basically a fraction of how much energy actually hits this second object. So I want some energy exchange between two objects, object one and object two. So again, some energy is coming off this surface A1, and again, going in all directions. So some of it's going to the right, some of it's going up, some of it's going left. But some of it is hitting A2, and that's what I care about. Same thing for object two. Some of it's going in all directions. Some of it's hitting A1. I want to know how much that is. So the amount of energy that leaves one surface and reaches the other is called the radiation view factor, Fij. It's also called the radiation shape factor, not to be confused with the conduction shape factor that we saw a month or two ago. Those values of S in the table, that's completely different. So shape factor for conduction, put that away. Anytime I say shape factor now, I mean this guy, the radiation shape factor, Fij. So Fij, fraction of energy, leaves surface I, reaches surface J. So total energy leaving surface 1 and arriving at surface 2. So EB for object 1, again, EB is just sigma T to the 4th. That's my total energy leaving surface 1 times the area, because again, EB is just sigma T to the 4th. There's no area in there. That's total energy per unit area. So multiply by its area, and that now gives me the total energy leaving surface 1. And then I need this fraction that hits surface 2, so I just throw in this factor, F12, and that's the total energy leaving surface 1, hitting surface 2. I can do the same thing for object 2. I have EB2 times A2, that's the total energy, sigma T to the 4th times area, leaving object 2. And then F21, so again, F21, how much energy leaves surface 2 and hits surface 1. So be careful with these, F12, F21, not necessarily the same thing. If both objects are black bodies, all the incident radiation will be absorbed. So net energy exchange, sigma T to the 4th, A1 F12, minus sigma T2 to the 4th, A2 F21 is my total energy exchange between objects 1 and 2. So generally what's going to happen is if one object's hotter than the other, the hotter object's going to emit more energy, and so the colder object's going to be absorbing more, hotter object's going to be emitting more, and those will eventually balance out. So I mentioned that F12 and F21 aren't necessarily the same thing. That's because they possibly have different areas. If they have different areas, then different amount of fractions are going to hit different objects. We'll kind of see this in some of the figures we see later. But what actually happens is the area times the view factor is the same. So A1 F12 is always equal to A2 F21. And so what I can do in the previous expression is take those factors out essentially. So A1 F12 I can replace with A2 F21 or vice versa, and then pull the whole thing out. So Q12 is A1 F12, and then it's just sigma T to the 4th for the two objects. Again, it doesn't matter whether I pull out A1 F12 or A2 F21 because they're the same thing. So really the last thing we need to do to start evaluating these radiation problems between two objects is to find the values of F12 or F21. So this has been done for several common orientations. Again, this is just basically, I have some object, how much of that object actually hits the second object. So that's really just geometry. But this has been done for parallel plates, cylinders, discs, and a whole bunch of things. And there's a whole bunch of different graphs and tables and equations, page 603 to 607 in the textbook that lets you calculate them. One thing to be careful of is which one you call object 1 and object 2, because again, F12 and F21 are not necessarily the same thing. So make sure you know which one you're dealing with and make sure you're doing the right ones. So the tables look something like this. So again, we have some geometry. So aligned parallel plates. So object 1 and object 2 are generally called object I and object J. Have some dimensions, X and Y, separated by some like L. Geometry for this is just some big, long, complicated equation, which no one really ever wants to put in a calculator, and I don't blame you. Same thing for parallel disks. So Ri and Rj, these two things should possibly have different radii. So if they have this, they're the same area, then obviously it doesn't matter which one's which. But if one's smaller than the other, then you think of it, if this guy's kind of small, he sees, or more of his radiation is going to be hitting this guy than this guy, because think of energy coming off the surface. Stuff going straight up hits him. Stuff coming off at an angle may or may not hit him. The bigger this guy is, the more that angle hits him. So that's why it depends on the area. That's why F12, F21 are not the same thing. So again, this guy has some equation. This guy is actually not a bad equation comparatively. So this guy I sometimes use this equation for. And then perpendicular rectangle, so common edge, 90-degree corner there. Again, dimensions, z, x, and y, depending on the areas, and the n, I, and j. So these are all gives you for I and j. So if I have an orientation like this, again, make sure I'm looking for F12. Make sure that 1 is this bottom surface and 2 is the surface up here, just to make sure that you have the orientation right. Again, big ugly equation for this guy. What I usually do for these big ugly equations is they also have graphs. So exact same scenario. They basically just plotted this big ugly function for a bunch of different values of z over x and y over x. So a bunch of different values. So find whatever the z over x value is. So just basically geometry in terms of these heights and lengths. Have a bunch of y over x lines. So find the right y over x line, find the right value of z over x, and then come over here, find your value of Fij. That's how I generally do it for these long, ugly equations. A lot of times you end up with a situation that's not exactly the same as in the textbook. And a lot of times what you can do is use geometrical analysis, as what I call it anyway. And so, for example, if I'm looking at this object here, I have some object number 3, 2 more objects, 1 and 2 down here. So this looks a lot like that case we just saw with the 2 plates being perpendicular to each other. I can break that down into a view factor for A3 and A1, as well as a view factor between A3 and A2. Now, this gives me the equation. F, I'm going to call 3 and 1, 2 in brackets. So 1, 2 is kind of my second object down here. So F3, 1, 2 is equal to F3, 1 plus F3, 2. So that you can do with pretty much any object. This is just an example of how to do it. Now, I would never actually calculate this equation in this form, because this F3, 1, 2, I can just call this A1 and A2 to one big area, and I can find that view factor straight from the table. So I never actually calculate it this way. But what I would calculate is this guy here, because this guy here is not in the table. I don't have a table with a hole in it. So if I want to find this guy with a hole in him, what I can do is I can take this big guy, F3, 1, 2, and subtract F3, 1, and that's going to give me F3, 2. So basically just take this equation, move F3, 1 over there, and that's going to give me F3, 2 based on 2 geometries that are in that table. So I can find those 2 guys from the table, subtract them, find this guy. So a couple examples. First one, I have 2 parallel discs, diameters of 50 centimeters and 20 centimeters, separated by a distance of 10 centimeters. I want to find the view factor between the 2 discs. So actually I want to find both of them. I want to find one going one way and one going the other way. So I'll do both of them. This geometry, I can use either figure 13.5 or table 13.2 on page 605 and 606. So that's basically, do I use the graph or do I use the equation? Again, for this guy, the equation is not that bad. And so I'll start off with that. And so F12 for this case is S minus S squared minus 4R2 over R1 whole thing squared, whole thing to the half power, divided by 2. For these, R1, R2, and S are, again, just geometrical factors. R1 is the radius of my disk divided by the separation between the disks. R2 is the radius of the second disk divided by the, again, the separation between the 2 disks. And then this S is another geometric factor between these R's. So 1 plus R2 squared over R1 squared. So for the first disk, disk of diameter 50 centimeters, that's what I'm calling object 1. So R1 is 25 centimeters over 10 centimeters, radius divided by separation gives me 2.5. R2, again, radius over separation, 10 centimeters over 10 centimeters gives me a 1. And then S, R2 is 1, R1 is 2.5, so plug all that in. 1 plus basically 2 divided by 2.5 squared gives me 1.32. And then plug that all into this equation. S minus S squared minus 4 R2 over R1 squared, 1 half power divided by 2. S is 1.32. Plug that in. R2 is 1. R1 is 2.5. Plug all those numbers in where they belong. And I get a view factor for this of 0.135. Basically 13%, 13.5% of the energy leaving the big disk hits the small disk. Again, I can do that same thing with the figure, figure 13.5. it needs a value of L over R1, which is 0.4. It's kind of the opposite of this big R1. It needs an R2 over L, which is, again, calculated appears to be 1. From that figure, I can find an F12 roughly 0.14. Again, the graph, it's not going to be quite as accurate as the equation. So, but close enough for my purposes. And close enough for exam purposes. Close enough for most homework purposes. There's 1 or 2 homework questions that is very, very picky about decimal places. They actually have it calculated at 4 decimal places, which is ridiculous. So they've obviously used one of those big long equations. So unfortunately, you might have to do that for one of the homework questions, but exam purposes, 0.14 is close enough. Use the graphs, good enough for me. Do the same thing for the second disk. So the smaller disk, diameter of 20 centimeters. Again, I can use the same values that I had before. For R1 and R1 and R2 get switched around. But what actually changes, so R1 and R2 are the same as what I had before, but what I actually want is, because I'm finding F21 now instead of F12, S gets switched around. So instead of being R2 squared on the top and R1 squared on the bottom, flip those two around. So the R1 and R2 values don't change, but the S value does change. And so I have 8.25 now, the S value. The other thing that changes is in F21. These guys are flipped around as well. So in the other one, I had R2 over R1. Here and now I have R1 over R2. So that gives me, again, plugging in those numbers, 0.844. So 84% of the energy that comes from the top surface of the disk actually hits the big disk, because again, the big disk is so much bigger on top of it that it's hard for this energy to get around it. Again, I do the same thing with my graph, and I can find an F value of 0.84, again, which is pretty close to that, so good enough for me. The other thing you can see, if you want to check your answers, is that I can take A1 to the area of the big disk times F12, 0.135. I can take A2, the area of the small disk, times this 0.844, and I can show that they're the same number, again, proving that A1 F12 equals A2 F21, which also kind of confirms my answer, which is kind of nice. So second example, I have a room that's 4 meters by 4 meters on the floor and then 3 meters tall. One side at 260 Celsius, the floor is at 90 Celsius. I'm going to calculate the net heat transfer between that wall and the cool floor. So in this room, all I care about is 2 sides. I care about the wall at 260 and I care about the floor. So I'm assuming all surfaces are black. So I have a black body, epsilon equals 1. So Q12, A1, F12 times my sigma T to the fourths. The difference of the two. I can also take A2, F21 if I wanted. Doesn't really matter. So what I need to find from this, areas are easy to find, but I'm going to need a view factor, either F12 or F21, and I'm going to need temperatures, or not temperatures, but emissive powers, sigma T to the fourths for both of them, which again aren't that hard to find. So the big thing about this is the view factors. EV1, sigma T1 to the fourth, so 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth, times the temperature, 273 plus 260, and make sure that's in Kelvin. So this is for the wall. So object 1 is what I'm calling the wall. That gives me 4,576 watts per square meter for the wall. The floor at 90, same deal, gives me 984 watts per square meter. Then for this configuration, figure 13.6, again, I can use a big ugly equation if I wanted to, but I'm not going to do that. So that's why I have this guy here. So I could use this big ugly equation, but I don't want to. I'd rather use this nice graph over here. So one thing I want to realize with this is that this is Fij, this is Fij in this orientation. So if I have my floor as this guy down here, that's object 2, and my wall is object 1. What I'm really finding from this graph is F21. So hopefully that's what I called it on the last slide. So Z over X, Z is the height of my wall, which is 3 meters. X was 4 meters. So that is 0.75. So I want to come down here, 0.6, 0.8. This line is 0.7. So 0.75 is between these two lines. So somewhere between these two lines is where I'm looking. And then y over x curve. So which one of these red curves do I need to be on? Y is 4 meters, x is 4 meters. So y divided by x is just 1. So where's the line that says 1? There you are, 1.0. So I want to be on this line. And I want to be halfway between these two lines. So come up halfway between these two lines, hit that red line, come over here, and that's pretty much 0.18 where it hits Fij. So F21 should be 0.18. I call that F12, that's completely wrong. That is F21. So this should actually be F21. You can change that. That's F21, not F12. I will change that in a minute. And then what I actually need here is A2. So did I use A2? Hopefully I did. 2 is the floor. Yes, so 2 is the floor. So I did actually use the floor, 4 meters by 4 meters. So I did actually do this right, even though I called it the wrong thing. So again, this should be A2, not A1, because the floor is 4 meters by 4 meters. The floor is object 2. So I luckily did that right. Again, my view factor F21 of 0.18, then my sigma t to the fourth, 4576 minus 984 gives me a total net heat transfer of 10,345 watts between the wall and the floor. So that's the basic steps of radiation, emissivities, black bodies, as well as shape factors. So those are the basics. Hopefully, they're all solved fairly easy so far, and we'll get into a bit harder stuff next class.